All right, so in this video, we are focusing on horizontal stretches and compressions. So this is what I want you to do when you're talking about horizontal, you're talking about the x coordinates. Okay, so I need you to be looking at the graph from a left to right direction. So if you notice this blue parabola right here, that is going to be like my parent function. And then I'm just going to show you how things can change based on the numbers that are being affected with the x. So if we take a look at an equation right here where we have y is equal to a, and then we have f of bx, and then plus k. Remember that we've already talked about vertical stretches and shifts. So the a and the k affect the y, but the B is going to affect the X, okay? Now, the idea behind how it affects the X is think about what we're trying to do here. What we're trying to do is we have a function and it's got some number in front of x, and we're trying to relate it back to the original function, like how did it change? So what we are trying to do is figure out how to um, see how we can get our b value. Like what do we need? These two guys need to be set equal to each other, right? So b times what is going to give you a 1 because we want our parent function always has a 1 in front of it. So in order to figure out what we are multiplying by, well, we would divide both sides by b, and then that is what is going to tell us what we multiply by. So if we take a look, we are going to be multiplying by 1 over b. And then, of course, if that number is greater than 1, um, well, the b value is bigger than 1, then it's compressed. If the b value is a fraction, it's going to be stretched because when you go and you multiply it by the reciprocal, then that's what's going to make it either bigger than 1 or less than 1. So let's take, for example, over here our green graph. Notice that our 2 is a number bigger than 1. And over here, it says that if it's bigger than 1, it's going to be compressed. Now, to me, that is kind of like something's kind of wrong there because if I multiply something by 2, I'm going to get bigger. I'm going to get a stretch, not a compression. And the idea is that you're not multiplying by 2. You have to take your 2x, right, your 2x squared, and it needs to look like 1x squared. So what you're trying to do is figuring out, I take my b value, which is 2, times what, and that's going to give me 1. All right, so what I need to do is solve for my question mark. I divide by 2, and my question mark is actually 1/2. So I'm actually multiplying by 1/2, which makes it a compression. So my x values are getting smaller. So if you think about it, if we were to take a look at this point right here, this y value stays the same. These two y values stay the same, but the x value was smaller. It was half of what it was before. So now let's take a look at the red idea, the red graph. Now this one says that it's stretched, and it makes sense because it looks like it's stretched, right? The x value that originally was here at 2 is now 4, okay? So my original, I multiplied it by 2, and I get to my new one. So let's take a look at what this is saying. So we have 0.5x squared, and my original needs to be 1x squared. So I'm taking 0.5 times what, and sometimes it's just easier to look at it as a fraction. 1/2 times what is going to give me a 1, okay? Because I want my coefficient to be a 1. Well, that means I've got to multiply by 2. And so my question mark, which is what I'm multiplying by, is 2. So this is going to be a stretch by a factor of 2. Okay, which means I'm taking every x coordinate and I'm multiplying it by 2. So let's take a look at what's happening over here with regards to a graph. All right, so we've got a population of apparently fruit flies, and the x is going to represent time, and this is the population based on time. All right, so the supposed scientist is comparing a population of fruit flies to a population that progresses through its lifespan twice as fast as the original. All right. So I'm going twice as fast. So if you have to make sense of this. You have to make sense in terms of um, are your X values shrinking or are they getting bigger? All right. In other words, this new population R is going to progress in 1 hour the same amount as the original does in 2 hours. So if this is the original, 2 hours, right? The new one, let's make it red, is going to produce that same amount in 1 hour, okay? And again, this original, which is 3, is going to produce that same amount in half the time. And let's try this one, 6. The original is 6 hours. Well, now my new one is going to be in half the time. So that's in 3. All right? So already I'm trying to make sense of the problem. All right, so what's going to happen here is it says to go ahead and sketch the graph of the population. Well, whenever you do a graph, it is very important that you pick beginning points, ending points, and anywhere where it turns. So this is my beginning point. I go in order from left to right. So this is point 1, this is point 2, this is point 3, and this is point 4. So I have my X and my Y chart. The first point is 0, 1. And let's just say 3, 3. Third point is 6, 2. And the last point is 7, 0. So when I was talking about changing the time, none of the X values are affected. I'm sorry, did I say that? I said none of the Y values are affected. It's all a matter of changing the time. So you're either stretching or compressing it. So I'm going to leave my Y values the same. And then we just talked about that my multiplying my or my X values, they're getting smaller. So I'm multiplying my X values by half as much. And if you think about this, this is trying to say this population here, I don't know, R, is going to be twice as fast, right? It's twice as fast as my original population. Okay, so that means I am multiplying my X values by 1/2. So obviously 0 times 1/2 is going to be 0. 3 times 1/2 is 3/2. 6 times 1/2 is 3. And 7 times 1/2 is 7/2. So I take those points. That point stays the same. This is half. We got 3, 2, because it's half of 0.3. Have this one here and 7. It's half, and you're here. And make sure this one had a curve, and then a line, and then a line. So you want to make sure that you keep the original shape. All right, so now let's talk about recognizing a horizontal compression. Okay, so we can see that the X values got smaller. So this is a compression. Okay. So what we want to do is match up points. Well, 0, 0 doesn't do me any good. All right, they both have 0, 0, so that's not any good. This one is 4, 4, but this one is, I don't know 4, so that's no good. So what I want to do is find a spot where I can compare those coordinates. So this is going to be 6, 4, and this one right here is going to be 2, 4. And so I am trying to look and see how my x's changed. Okay, so we could see that g is 1/3 of f. Okay, so what we want to do is figure out how I can write the equation for that. And so we could have g of x is equal to the f function and then 3x. Okay, so that if I were to multiply, I'd multiply by 1/3. Okay, so another way to look at this is I don't know my b value. So I know that bx times 1/3, okay, is going to equal 1x. Okay, remember that's kind of like this idea right here. F of bx needs to equal f of x. Well, I don't know my b, but I do know that if I take that b and I multiply it by its reciprocal, then I'm going to get the 1. And I just put the x there just to keep it, but we don't need to do that. We can get rid of the x. So now my question is, what is going to be my b value? So if I were to multiply this side by 3, I can get b is equal to 3. So that is going to give me my equation. G of x is equal to f of 3x.